Good morning, everyone. Thank you very much for coming here this early. And today we're going to talk about metaprogramming and introduce a little-known aspect of Hilt called Hilt extensions. So let me start with a very quick introduction. My name is Fabian. I work as a senior Android engineer at Babel, a language learning app here, based here in Berlin. And I've been doing Android since the KitKat days. And during all these years, I've played kind of dual roles in my career. I've been working both in feature teams and in platform teams. And two main areas have spiked my interest more than anything else. So during these years, I've come to be interested in developer experience and scalability in large teams. And this talk is actually inspired by some work that I did with the excellent team of Android platform engineers at Payback. So the main topics that we're going to look at today will be the following. First, we'll start to look at and try to define what metaprogramming really is. It's not related to the company previously known as Facebook. Secondly, we will try to answer the question of why being lazy is actually a good thing in our profession sometimes. Then we'll look at what Hilt actually has to do with all this metaprogramming stuff. And finally, we will write a simple Hilt extension with the help of KSP, Kotlin Symbol Processing. So let's start with the first topic. What is metaprogramming? Well, first time I ever encountered a word that started with this meta prefix was actually metaphysics. So in physics, we study nature, right? And in metaphysics, you study the nature of nature, which is this branch of philosophy that I suspect that nobody knows what they're talking about when they talk about this. And actually in ancient Greece, physicists were known as philosophers precisely because of this reason. They were studying both physics and metaphysics at the same time. However, with the passing of time, physics and metaphysics split into two different disciplines, right? So nowadays, they are completely different things. So it looks like we can slap meta in front of a word and create a new one out of thin air. At least that's what humans have been doing since the antiquity. So let's do the same thing here. In a comic book, an artist will draw a balloon on top of a character's head to kind of tell the reader that someone is thinking. So what about, like, for example, me on a date? If I think about what the other person is thinking, right? Am I meta-thinking? Well, you can say so, because here I just took thinking, put thinking in front of it, so I did this recursive step one time, and I invented a whole new word, right? Great. So, it looks like slapping meta in front of a word, you can create a new one out of thin air. And it was only natural that once programming started popping up in the vocabulary, language nerds would do the same thing, and metaprogramming appeared. And if you search the internet, this is one of the definitions that comes up. And I don't know about you, but I tend to lose interest in these long definitions about mid-sentence. So don't panic, we'll try to make it simpler. I'll try to give a shorter and more concise definition. And this is what I came up with. Metaprogramming is just a fancy term, which means writing programs that can read, generate, and modify other programs, including themselves. All right, but if that wasn't clear enough, don't panic, we can make it even simpler. Let's use emoji. So, programming, you write some code, which ends up running on a user's device. Metaprogramming, you write some code, that code writes some other code, and that other code ends up running on user's device. So here again, you add a recursive step in front of something that you do every day, and we have invented a whole new word. All right, so this recursive step in Kotlin has two different flavors. The first one is reflection, which you can hook into when you basically start using this Kotlin reflection library. If you've used the Moshi library just when it came out, basically what Moshi was doing was it was using reflection. And with reflection, you can inspect the structure of your program at runtime. So for example, you can look at the values of the parameters of a data class, the properties. You can assign values to those properties and even modify things at runtime. The second one is code generation. and we use Kotlin symbol processing to do that. The Kotlin compiler actually goes through several phases of analyzing and compiling your source code before it generates the bytecode. And during these compilation phases, during one of those actually, you also get the chance to read the structure of your program, generate new code. However, you're not allowed to modify the current program. So if you've noticed, there is only a slight difference between these two flavors of metaprogramming. In reflection, you can read, generate, and modify the current program. In code generation, you can only read and generate the current program. However, if this is still too confusing and you leave this talk learning nothing new, very conveniently, today, once I was coming to this conference, I learned that there will be 2 other talks today, which will go more in depth for reflection and for code generation more specifically. So here we don't have the time to go through what reflection is, what code generation is, so make sure to attend these talks. All right, so we now know what metaprogramming is. We write some code, that code writes some other code, and that other code ends up running on a user's device. Let's see why being lazy is a good trait in our profession. So the backstory of why I decided to do this talk in the first place started when we went through this constant increase in scale in one of the projects that I used to work on. And this is just an example here. So when you start developing an app, typically you have only one app module. Everything goes well at the start. You start shipping features to your customers. Everybody's happy. You're a small team, maybe 1, 2, or 3 developers, and you know the code base all through and through. However, after some time, your team grows in developers, your code base grows in size, you get stuck trying to push out features while trying not to step on each other's toes. So what do? Well, as a starting point, you think that separating the code base in different modules would be a great idea, so each team can work as independently as possible from one another. And each team is responsible for a certain number of modules that they maintain. So that's great, you start shipping faster again, the pace starts picking up again. However, after some time, you run into different kinds of issues. So you have to take now into consideration the dependencies between each module, how to consume one module from another, otherwise you start running into this pesky circular dependency issues that Hilt does a great work of showing you in your logcat, right? And you decide to introduce some ground rules regarding module hierarchy. One common way to do this is you split your feature modules into submodules. Basically, you break up the part that is exposed from the part which are implementation details. So, schematically, it would look something like this. Implementation modules can only depend on other API modules. And the app module, in the end, which previously had all the code, now it's just an aggregator for all of them. So, if we take a look at what an API module might look like, it's something like this. Mostly interfaces, they are explicitly public, they represent the services that get consumed by other modules. So if someone imports this API module, they just see this simple interface. However, the behavior of that interface has to be implemented somewhere, and that is what the implementation module is for. So here we implement the interface, and after that, if we have a dependency graph in our app, we somehow need to tell the dependency graph that whenever someone requests an instance of this answer calculator interface, please provide the implementation class, which in this case is the deep thought computer. And in Hilt, there is this nifty way to achieve this by declaring a binding method, right, in the Dagger module, and that module will be picked up by Hilt, and it will be installed in one of Hilt's components. So, basically, what we need to do is, in a way, try to declare a link between an interface and an implementation. However, as you can see, implementation classes also have a lot of dependencies which you need to inject into them. So here, for example, we need this other class called the Union of Philosophers to do some protesting before deep thought tries to calculate and think and calculate the answer. And since the Union of Philosophers resides in a different module, what we need to do is we need to use the interface, which is declared now in the other feature modules API submodule, right? So remember here that the rule is implementation modules can only depend on the other API modules. And more specifically, this is not allowed, right? So we cannot pull the implementation directly from the other features implementation module. So similar to the last example, the team that is responsible for this other feature needs to write the implementation of the interface that they expose. And they do this in this implementation module. And again, they have to also write this ceremonial declaration of the link that whenever someone asks for this interface, please give them this implementation. So far, we did this twice. However, here again, we go and have the same problem. In the constructor parameters of the implementation class, it looks like there is some other dependency that we have to inject from somewhere else. So, and who knows what that dependency, how many other dependencies it has in turn. So I see a pattern here actually, and since I'm extremely lazy, eventually I grew tired of writing the same module over and over again and decided to check whether there was a simpler way to do things. So being lazy was a big motivator. And it's completely fine, for example, if you do this for a small example app. So in this example, there are 4 modules with 1 binding each. So in the end, you write 4 extra Dagger classes. It's not the end of the world. But besides being extremely lazy, there is also a more pragmatic reason why we don't want to write these classes ourselves over and over and over again. And the code bases that we usually work on, they are not this nice example with 4 modules with 1 binding each, but it's more like 100 modules with 10 bindings each. So in the end, we end up writing 1,000 extra classes. So I don't know about you, but as I said, I'm extremely lazy. I really don't like writing the same thing over and over again 1,000 times. So let's try to imagine a better way that we can do this thing. Let's start by just scratching, writing this ceremonial boilerplate just to satisfy our dependency graph. And we can start imagining a better solution. And whenever I decide to start looking for a solution to a specific problem, I start with the most simple API that I can think of, which just gets this job done. It might not be what we end up in the end, but the simplest solution that I can think of is one annotation on the implementation class, and that annotation somehow takes care of establishing the link between the interface and the implementation. So wouldn't it be great if we could just write one annotation which takes care of this binding for us without us manually writing it ourselves? Oh, I know. Well, we mentioned this before. We can generate code with KSP. It was one of the flavors of metaprogramming in Kotlin. So what we're going to do is we're going to take that annotation, run it through some code generation, and in the end, that code generation is going to produce this Dagger class that will establish the link. So in the end, what we're going to do today is replace one class with just one annotation. So we want to use code generation so that we can replace a class with only one annotation. But why do we need to take Hilt so much into consideration? What does Hilt have to do with this? Well, during university, in compiler class, I always fell asleep. So this is just a theoretical diagram of what happens during Kotlin compilation. Fortunately, JetBrains has some office hours, I think, in this conference. So if you need more details on the Kotlin compiler, go to them, ask them. However, the Kotlin compiler goes through several steps, right? Takes your source code that is written by you in your source files, It goes through several syntax and analysis and validation, and then at some point it creates a typed representation of your source code. Then there is a specific place during the compilation process that you can extend the compiler in a way. So it creates this typed representation of your code, and then it calls your KSP plugins and says, here's a type representation of the source code, take this source code, read it, and then you can generate even more code from the original one, and then I will take care of the rest of the process. And both the code that was there in the beginning and the code that you generated during the KSP plugin compilation steps will end up being produced as bytecode. So we know that when we import Hilt in our projects, we use KSP. And Hilt itself is a KSP plugin. And we said that we want to use code generation to have this auto-bind annotation processor, right? Or a KSP plugin. So we might wonder, since they are both KSP plugins, which runs first, Hilt or auto-bind? Will Hilt pick up the code that we generate and wire it up in the DI graph, or it will miss our code and generate the Hilt components without picking up our code? Well, as it turns out, the order in which different KSP plugins run is undefined. So here we might run in a chicken or an egg problem. However, there is a solution to all of this. Buried deep in the depths of the online Dagger documentation, the solution is called Hilt extensions. So, in order for Hilt to pick up your generated modules, what you need to do, your extension annotation, which in our case is auto-bind, you need to annotate your annotation. Use a meta annotation called generates root input. And as you can see in the bottom of this page, there is a warning which tells you that if you fail to use this meta annotation, you cannot be certain that Hilt will pick up your module and it will install it into the respective component. So this chicken and egg problem is also mentioned here explicitly, and it's super convenient in the bottom of the page. So, all right, in the worst case scenario, we said that Hilt would run, generate the components, and it will miss whatever we're producing here. So what we need to do is this. We use this meta annotation, and then we make sure that Hilt will wait for us. We will generate our modules, and afterwards Hilt will then start compiling all the generated code. And basically it will pick up the output of our KSP plugin and install the modules that we generate into the components. So let's take a look at how we should declare our extension annotation. Well, it's pretty simple. We just declare an annotation class. We annotate it with this meta annotation called generates root input. And ladies and gentlemen, say hello to a real Hilt extension. So let's take a step back and try to understand what we're trying to achieve, right? The module that we want to generate is this one. It has 3 different types that change with every link with every class that establishes this link between an interface and an implementation. So they are like color-coded here, and as we can see, we have an interface type, we have an implementation type, and we have a Hilt component. And above, one type is missing, right? Type information is incomplete, so that we don't have all the information in the implementation class itself in order to be able to generate this. So somehow it looks like we have to carry over this information into our auto-bind annotation constructor parameters. And it looks like, in the end, we cannot have this super lazy ideal API that we envisioned in the beginning by using just one annotation after all. So if we go back to our Hilt extension, we see that we need to provide a constructor argument so that we have all the type information. However, since constructor arguments can have default values, and I suspect in most code bases what you want to do is just install into this singleton component. So the singleton component is the most widely used component. We can put this singleton component here as the default value. And therefore, what we can do is we scratch that from out-of-bind, and we are able to, satisfy our extreme laziness and just use one annotation to generate the whole thing, at least for most of the use cases. So here it is. We know that this thing is doable after all, right? We have all the type information encoded in our implementation class and in our out-of-bind annotation. So far we kind of talked the talk. We know that we can replace a complete Dagger class that serves as a binding glue between interfaces and implementation. We have the complete type information. Now let's try to walk the walk and see how we can actually write a KSP plugin to build a Hilt extension. So the following slides will actually have a lot of code. So in case you're still awake and start falling asleep mid slides, don't worry, I will upload this all somewhere. So there will be more info in the end, actually. The 4 dependencies that we need to do our annotation processing are the first one, the out-of-bind Hilt extension that we declared somewhere. The second one is Hilt itself, so we can refer to Hilt's annotation. The third one is KSP itself, so that we can actually hook into the Kotlin compiler processing steps. And the fourth one is Kotlin Poet. KSP by default provides you an API to generate code. However, that API is very low level, so the fine folks at Square have actually done us all a favor and created a more higher level API to specify how you want to write the Kotlin code that you want to generate. So this is just ceremony. So in order to hook into KSP, we have to implement this symbol processor provider interface. And this symbol processor provider interface actually returns the actual symbol processor, and it gives you like a hook into the compilation environment via this environment parameter. So not really important. What's important here are these 2 classes. The first one is the actual out-of-bind processor, which is responsible for reading your code base. And the second one is the bind module code generator, which is responsible for generating the class that we are too lazy to write ourselves. So if we take a look at the out-of-bind processor, as we said, it implements the symbol processor interface. So this is where the actual KSP starts running. And it has only one method that you need to override. And this method takes a resolver type. And with this resolver type, you can do things like look all the declarations in the code base which are annotated with out-of-bind. Then we do a little validation step. We make sure that everything that is not a class that is annotated with out-of-bind is filtered out. So maybe someone annotates an interface. We don't know. This is just a simple validation steps. And afterwards, for each of the class declarations annotated with out-of-bind, we want to generate a Dagger module. Therefore, we pass along the out-of-bind annotated implementation to the class that will do the code generation. So far we have found all the class declarations in code which are annotated with out-of-bind, and we have passed all the class declarations which are annotated by this out-of-bind to the code generator. Before we go into the code generator, it's always a good idea whenever you do some annotation processing or KSP plugin to look at the end product first and try to understand the structure of the code that we want to generate. We can summarize this in kind of 3 steps. First one is a single file, which is named implementation declaration supertype module, basically a single file with a name derived from the interface. The second one, the second step is a single abstract class, also with the same name, annotated with this module from Hilt and install in. And the third step is we want a single abstract function, also with the same name, annotated with binds. And this function takes one parameter of the type of the implementation, and the return type of this function is the supertype. With Kotlin Poet, the API for generating Kotlin code is declarative. So in order to generate our module, we first write the specification of a file. So basically what a file looks like is just a file spec. It has a builder. The builder has a package name, a file name, and then we add our class spec inside this file. We build, and that write to is just basically telling Kotlin Poet, here's the KSP environment, take your high-level representation of what we said here and translate it to whatever KSP is expecting. So this is the first step. We want a single file with this specific name derived from the interface. Step 2 will be the generation of a Kotlin class within that file. And again, we go through a type spec, which is a single abstract class named from the interface type, annotated with module and install in. And basically, that's what the type spec does. It generates this, this class. And if you want to look like line by line, basically, we declare our class name. We say it wants to be abstract. We add this module annotation. We add this install in annotation. And in that install in annotation, we take some, we take the component from our out-of-bind annotation. And that's it, right? Step 2 is complete. Now, let's look at step 3, generating the function spec. Again, very simple, declarative API. We want a single abstract function named bind and then interface type module, annotated with bind, one parameter of type implementation, and we want to return the super type. That's what the third step will actually produce. And if we go through this line by line, again, we just declare a function spec with a certain name. We make it abstract. We add these binds. It has one parameter of the implementation type, and it returns the interface type. And that's it in all 3 steps. Okay, there is a demo, but I'm not sure that I can make it. No? Let me just try to. Okay, wait a second. Okay, let's just forget the demo. It's like, I didn't pray to the demo gods before, so probably that's the reason. All right, so before we go into questions, thanks a lot for coming. I really appreciate it. And feel free to send me a connection on LinkedIn. I will eventually post the code and the slides there. Haven't had the time so far, so that's it. Thanks a lot.